Let me thank Professor Pollack for kindly inviting us at this water conference. But above all, I have to thank for his astonishing discovery, the Exclusion Zone. Our group had the input to continue their studies. We enjoyed it so much, and yet we do. Iterative procedures to highlight the formation of molecular aggregates in pure perturbed water. Our experimental data indicate that we are facing a new phenomenon. Your theory is crazy, but it's not crazy enough to be true, Niels Bohr. We hope our hypothesis to be crazy enough to be true. When a thing was new, people said, it is not true. Later, when its truth became obvious, people said, anyway, it is not important. And when its importance could not be denied, people said, anyway, it's not new. William James. This presentation will illustrate 4 different methods to perturb water. All of them produce very similar systems with quite peculiar properties. We call all of our waters iteratively perturbed water, or IPW, followed by the initials of hydrophilic polymer that induce the variations. The first method is the classical one employed by homeopathic medicine that produce extremely diluted solution, EDS. The second one was obtained the first time in our lab, and the third and fourth methods employed the discovery of Gerald, the exclusion zone. Briefly, a sheet of Neptune is placed in a Petri capsule made of polystyrene. Water is added in order to form exclusion zone. With a soft mechanical procedure, we try to shift clumps of the heat zeta into the bulk water, and with a bit of luck, that succeeds. The IPWN liquid shows physical-chemical properties that are very different from those of the initial waters. And here you can read the method. When we use another polymer, hydrophilic polymer, HC, hydrophilic cotton, we obtained the same results. Neptune is a tetrafluoroethylene polymer with side chains bearing sulfonic groups. Hydrophilic cotton is cellulose. The 2 polymers are very stable and practically insoluble. In the next slide, I will describe the physical-chemical properties of IPN, which are quite different from those of ultra-pure millicube water. And the next 3 slides contain graphs showing the linear trend of pH as a function of the logarithm of electrical conductivity, and for 3 waters perturbed by hydrophilic polymers such as hydrophilic cotton, Crabion, and Neptune. Crabion is a mix of cellulose and chitosan, a cellulose derivative. The water in contact with hydrophilic polymers of Neptune, cotton, and Crabion have changed and no longer match the chemical and physical parameters of the used millicube water. varied parameters: pH, specific electrical conductivity, heat of mixing with acid and bases, density, IR, UV absorbance, fluorescence microscopy, light scattering, circular dichroism, fluorescence spectra, and so on. And the linear trend of pH as a function of the logarithm of electrical conductivity obtained using as perturbing polymer hydrophilic coating. And such linear trends in log-log graphs hint a fractal nature of the perturbations induced in the liquid. When I used hydrophilic cotton as a perturbing polymer, the line has a positive slope, alkaline solution. The electrical charge of the aggregate is positive. For Cryon, the slope of the trend is practically null, neutral solution. The aggregate electrical charge is null. When the Nafion polymer is used to perturb water, the slope of the trend is negative, acid solution, negative charge of the aggregate. In this figure, we come full circle. It shows that the nature of a hydrophilic polymer is essential in determining the variation of physical-chemical parameter of the iteratively perturbed water. Our work hypothesis is the formation of molecular aggregate, as of now unknown composition. This behavior highlights the extraordinary versatility of water in responding to physical perturbation, even those of low intensity. The density parameter here reported as a log of density is a function of a logarithm of conductivity, also follow a linear trend in a log-log graph. And this additional property further reinforces the hypothesis of fractal nature of the aggregates. It is interesting to underline the large difference in the trends of density as a function of electrical conductivity between different perturbing hydrophilic polymer. In red, the perturbing polymer is hydrophilic cotton. In blue is Nafion. Note the large differences in the slopes of the trends relative to cellulose polymer, HC, compared to the Nafion one. The higher slope trend induces the formation of aggregates that render the liquid alkaline, and the lower slope render the liquid acid. Still pertaining to the liquid phase of IPN and EDS, the next slides contain the first ever photograph of a molecular aggregate of micrometric size in pure water in solution. To obtain such images, nanospheres of polystyrene soaked in fluorescein are inserted in the liquid sample. The sample with the nanospheres is then illuminated using UV light, and finally, using optical microscopy, we obtain the following images. A remarkable, clear image of an aggregate is visible. This is an IPWN aggregate using Nafion as hydrophilic polymer, and was published in. The same happened if you use a solution obtained with the homeopathic method. In this case, we show you the aggregate of aspirin 12CH, and also published in the same year. Molecular aggregates in the liquid phase can be seen. As many of you will know, circular dichroism spectroscopy is a widely adopted technique in the study of biological macromolecules. And in next slide, the CD spectra of some very well-known biological macromolecules are shown. This was the figure you find in all the books of biological physical chemical. The CD spectra provide important information on the secondary structure of protein, polypeptides, and DNA. The shape of CD spectrum provides information on the presence in solution of optical active polymers and on their secondary structure, alpha helix, beta sheet, or random coil. Naturally, these macromolecules have asymmetric center. Of particular note for us is the beta sheet spectrum in red. And this slide reports the CD spectra obtained of some of our perturbed water. All of them produce highly significant CD spectrum that allow to characterize the supposed macromolecule, have a secondary structure typical of a beta sheet with variable twisting. The wavelength corresponding to the minimum in the curve is 250 nanometers. This slide shows the circular dichroism spectra of a liquid obtained using hydrophilic cotton, cellulose, as perturbing polymer. Also in this case, we found a secondary structure that simulates that of a beta sheet. Compared to the previous spectra, the intensity is lower, but the wavelength of the minimum is the same, 215 nanometers. This slide contains the CD spectra of liquid obtained through homeopathic procedure. They are EDS solutions, extremely diluted solution. The fact that also in this case, very similar to the preceding cases, a beta sheet was obtained underlines the general behavior of iteratively perturbed water. It is worth noting, though, that the wavelength of the minimum is located around 225 nanometers, very different from the previous one. There are similarities, but also peculiarities in this. A common feature between IPW and solution of biological macromolecules is the denaturation process. It is common knowledge that a biological macromolecule, a protein for instance, can exist in the native state or in a denaturated state. In this native state, it can carry out its biological activity in biological systems. In the denaturated state, instead, it loses this possibility. One of the standard methods to denaturate a biological macromolecule is to increase the temperature of the sample. Usually a temperature between 16 and 19 centigrade, it is enough to obtain the denaturation. And this was what happened. In this slide, we show how the prolonged thermal treatment can chill any circular dichroism effect on IPWN. What has been said till now demonstrates a staggering similarity between IPW, perturbed water, and a biological macromolecule. This parallel does not end here. In this slide, we show the CD spectrum of the sample, black curve, simple, keep it at 90 degrees for 25 hours, in red is flat. We have obtained, but it was needed 24 hours at 19 degrees to denaturate this unknown macromolecule. This slide contains the CD spectra. Sorry. Sorry. Okay. In this slide, we show the CD spectra for a perturbed water obtained using hydrophilic cotton cellulose when undergoing a thermal treatment aimed to the denaturation of the secondary structure of the known polymer. You can appreciate that the polymeric structure obtained when employing a natural polymer, cellulose, is much more resistant to the denaturation process than when using Nefion. In fact, you can see that you need about 72 hours to obtain from the black curve, the blue curve, in which the CD spectrum is totally loosed. In the next slide, we see the fluorescence spectra of 3 samples, one obtained with Nefion, the other one with hydrophilic cotton, and the EDS. This was the fluorescence spectra for perturbed water using Nefion as perturbing polymer. It is in a clear spectrum with 2 sharp maximum at about 350 nanometer. And this was the fluorescence spectra of liquid obtained perturbing water using the natural polymer hydrophilic cotton. Very, very different. 2 large maximum, one at about 315 nanometer and the other one about 425 nanometer. As you can see, we do get fluorescence spectra that are not flat. The similarities between the 3 perturbed waters and the biological macromolecules continue to surprise us. There is a feature found in all 3 spectra. The presence of 2 maximum, and apart from that, there is a very large difference in both intensity and the wavelength at the maximum. And this slide better show you the very different fluorescence spectra obtained by 3 different perturbing methods, using Nefion in blue, using hydrophilic cotton in red, and using the methodology of homeopathic medicine in green. The liquid contains a macromolecule that behave similarly to a biological macromolecules. Otherwise, it is impossible to have a spectrum of circular dichroism or a spectrum of fluorescence. To obtain a solid-state sample of this macromolecule, it is sufficient to evaporate at room temperature and pressure a few drops of liquid, as is customary for atomic force microscopy or normal optical microscopy. Another method consists in removing bulk water using a lyophilization procedure, freeze-drying procedure. And we show some of the solid obtained in this very long study of this strange perturbed water. And this photo shows the solid deposit found after lyophilization of perturbed water using Nefion. Naturally, one of the most striking examples in terms of quantity of the solid. This was the one obtained perturbing with hydrophilic cotton. This one perturbing with the method of EDS, homeopathic system. This using ribon as polymer, perturbing the polymer. This one using the normal paper filter cellulose. And thermogravimetry. This technique consists in measure the loss of weight of a solid at increasing the temperature. Conceptually, very simple. It gives information on the thermal stability of the product. Yet another example of the versatility of water when affected by iterativity perturbation of physical nature have no low energy. This slide contains thermogravimetric analysis, TGA, in green, a piece of paper filter, cellulose, simple, a solid, you take a piece of paper filter and made this analysis, thermogravimetric analysis. In black, the localized solid obtained perturbing with paper filter, and note the extraordinary different behavior of the line of the perturbing polymer as respect to the line obtained when the solid is obtained lyophilizing the perturbing water. The system and perturbed system have not lose weight until it reach about 350 centigrade, the normal stability of a CC carbon atom, and then reduced to zero. But the solid obtained by lyophilizing the liquid obtained using this polymer as perturbing is very stable and very different from its behavior in black. And when we reach 600 centigrade, the 50% of the solid is until stable, not go away. This table reports the percentage in the weight of the element C, H, and O in the solid obtained by a lyophilization of the liquids perturbed by some hydrophilic polymers and the corresponding perturbed polymers. It's easy to spot that the main differences between the lyophilized solid and the perturbing polymer are in an oxygen column. This was the content in the lyophilized polymer, about 19%, and this was the content of the polymer, the perturbing polymer. This is what the low content of carbon obtained already. This was the content of carbon in the first column, very low, also compared to the content of carbon in the perturbing polymer. It is another substance with different thermal stability as respect to the polymer. It's not the polymer. It's another new substance until now of unknown composition. And these micrographies are obtained through a standard optical microscope, maximum 500 magnification, letting a drop of IPW water evaporate on the glass. The fractal nature of the solid is clear. This one was obtained using hydrophilic cotton as perturbing polymer. This one using carbon as perturbing polymer. Very different, but all as fractal nature. This was by cellophane, a very new a derivative of cellulose. And this was using nephew. And having the famous pure water, fresh water, in dispregiative manner, the solution of homeopathic medicine is shown here in its full splendor. Also, in this case, it's possible to have this very important information. A new material was obtained whose chemical composition is oxygen, hydrogen, and carbon. It can exist in the liquid phase in aqueous solution. The liquid contains a macromolecule that behaves similarly to a biological macromolecule. It can exist in the solid phase at room pressure and temperature. It is probably a new kind of polymer obtained perturbing water. In all important transactions of life, we have to take a leap in the dark. William James. A request. If some of you can permit us to measure optical rotatory dispersion measurements, thank you for attention.